So it turns out classical relativity is simply not correct enough. But it is pretty good for slow stuff. And so whenever you are talking about or doing physics where speeds of objects and relative speeds of observers are all slow compared to the speed of light. So that this is when classical relativity is likely good enough, honestly. So both the objects and the relative speed of different frames of reference are slow compared to the speed of light. You have to qualify this, honestly, and so is half the speed of light slow enough, or is 3/4 the speed of light slow enough? That turns out to be an engineering question, quite honestly. So you have to understand how tight your tolerances are before your technology goes wrong because you weren't using the right relativity, that it wasn't correct enough. So the gist of the story is Einstein and other scientists around the early 1900s came up with something that is simply better, and that's referred to as the special relativity. And the special relativity is also going to work at slow speeds, but it feels more clunky, and its corrections are small when stuff is slow, but its corrections to classical relativity are actually quite large when things are moving closer to the speed of light. Okay, so so the thing I need to describe first is I want to say one of the really nice things that classical relativity does in particular is there is a frame independence for laws of physics. And the laws of physics that I'm talking about are the conservation principles. So conservation of momentum, conservation of energy, conservation of angular momentum as well. But this frame independence is, you have to be really careful. It's not any reference frame. The reference frames are called inertial reference frames. So it's inertial frame independence for laws of physics. This is a big deal. So first thing I want to describe is what is an inertial reference frame. So the quickest way to say what an inertial reference frame is to say a physicist in an inertial reference frame will see Newton's laws of motion. What this means is that, for example, if the net force on an object is 0, then the acceleration of the object is 0, right? Another sort of consequence of Newton's laws is actually these conservation rules up here. So if F net on an object is 0, then that object's acceleration will be 0, which implies that that object's momentum will not change in time, right? Interestingly, like in particular, if the velocity doesn't change and the mass of the object has no reason to change, then there is no reason for the momentum of that object to change. And also, it means that there is no change in the kinetic energy, because if the net force on an object is 0, then there is no work being done on the object. And so the idea is the net work is associated with the change in the kinetic energy, and here there is no change in kinetic energy. So let me give you an example of a non-inertial reference frame. So example of non-inertial, so I'm going to abbreviate this as NI, frame. So pretend that I have a massive ball hanging from a string connected to some ceiling, right? And there is a physicist who is in free fall. So here's the physicist a little bit of time earlier, and they are falling down towards the Earth, say. And here is the physicist a little bit later, they're moving faster, right? The physicist is accelerating, so the physicist's point of view, or the physicist's reference frame, is an accelerated reference frame. And what this physicist notices is that even though the net force on M is equal to 0, the physicist notices, right, as the physicist falls past the object, according to the physicist, the object is accelerating up past the physicist. And so under the influence of no net force, this massive object is gaining kinetic energy, it's gaining upwards momentum, and in fact also has an acceleration. So so this falling physicist who doesn't realize that they are in an inertia or non-inertial reference frame would arrive at some physics that would say that this mass, even though it has no net force on it, has a reason to have its motion change, which violates Newton's laws of motion. So Newton's laws of motion are the laws that any physicist would arrive at if they were in an inertial reference frame. This is the idea of an inertial reference frame. Okay. So the idea is for the rest, so inertial reference frames are where the laws of physics tend to get sussed out. Okay, so let's move on. I'm trying to get to why relativity turns out to not be correct enough. That is, classical relativity is not good enough. Okay, so let's think about a classical picture of light. So this is the phenomenon of light used to be conceptually understood as a wave. So the classical picture of light is it is a wave disturbance that is carried by I'm going to leave a big space, medium called ether. So this was the reason that people thought back in for a long time. The idea is a wave disturbance is a disturbance that's carried by a mechanical medium of some sort. So mechanical mediums are mediums under tension that are made in some way out of something that has inertia, some massive component in a sense. And there is the idea is there is this substance referred to as ether, and if you can electromagnetically disturb the ether, then that disturbance travels away from where it was created at the speed of light as a disturbance of this mechanical medium. The mechanical medium is trying to remain, in some sense, at equilibrium, and if you disturb it nearby, then that equilibrium is disturbed by a wave that travels through, and then after the wave has traveled through, that disturbance is no longer located where it used to be, is the idea. And the speed at which the disturbance is carried away from its source is dictated by how much tension this material has, the medium, and also how tightly, how sluggish or how inertial is the material of the medium. So as an aside, let's remind ourselves about sound. Sound is a wave disturbance, and let's consider sound in air, right? Because you can have sound in solids and liquids as well, and as well you can have sound in plasmas. Actually, I'm not a plasma physicist. So I think they call it sound waves in plasma. But anyways, so let's talk about sound in air. Air is a mechanical medium. It's not called the ether, it's called the air instead. And so as an aside, so this is a bit of a temporary aside, let's say that I have an air mass, right? So here is a bunch of air, and this air is sort of all stationary with respect to itself. So over here in the air there's not any wind, when over here there's not wind, for example. It's just all the air molecules are in some sense stationary relative to each other. Okay, and in this air mass is an airplane. Right, so this airplane flies on the air mass, and hanging from the airplane is a speaker. Right, this thing right here is a source of disturbances. The idea is a speaker, right, is going to play sound out of it, and I'm going to draw some sound waves. So in the back of the plane, since the plane is flying, let's say towards the right, inside of the air mass, the sound waves that it creates are spaced widely apart, but the sound waves individually travel all at the same speed on the air mass, because it's the air mass that carries each of these disturbances. And in the front of the plane, these disturbances are a little bit closer to each other, and this is called the Doppler effect. Right? It's because as the plane flies forwards, it causes a disturbance that travels outwards, but as the disturbance travels outwards, the plane advances and creates the next disturbance a little bit advanced over and to the right. And so it bunches together, it shortens the wavelength of the sound waves in the front, and it lengthens the wavelengths of the sound waves in the back. But the sound waves are individual disturbances on the air mass, so the velocity of the sound waves relative to the air mass, right? So this is, let's shorten this to AM, air mass, and that's a V sub S, air mass, right? For typical conditions, this is like 340 meters per second, for example. So that's the that's the speed, right? The magnitude of the velocity. It's the speed of sound on the air mass. It's 340 meters per second for all of these. What changes, though, is the wavelength in the front versus the back for a source that travels through the air mass. So we could say, I just made, so let's call this the airplane, right? And we'll call the plane P. So we can say that the velocity of the plane with respect to the air mass, right, is an interesting velocity. It's how fast the plane flies through the air mass. And this is the velocity of sound with respect to the air mass. And so you can do things like this. You can say that the velocity of the plane, the velocity of sound relative to the plane, if we use our velocity addition formula, it's the velocity of the sound with respect to the air mass plus the velocity of the air mass with respect to the plane, right? And remember, when you switch the order of indices, you pick up a minus sign. So this is the velocity of the sound with respect to the air mass minus the velocity of the plane with respect to the air mass, right? So what this means is you could probably follow it through yourself. I'm just going to cut to the chase. In the front of the plane, what you get is that the velocity of the sound with respect to the plane has a speed that is less than the velocity of sound with respect to the air mass. So that is, the airplane will measure the speed of sound to be smaller than 340 meters per second. So the plane looks down at these sound waves, and because it can somewhat keep up with them, you notice a speed something like maybe 320 meters per second if the airplane is traveling at 20 meters per second, which is quite fast, right? But in the back of the plane, observers on the airplane look at these sound waves headed in the opposite direction, and they discover that the velocity of the sound with respect to the plane is going to be a bigger value than 340 meters per second, right? So what you detect, so what the airplane detects, because it's putting these sound waves onto the medium but traveling away from them, is it sees a speed like 360 meters per second, right? Okay, so this plays out exactly the same way with light. So instead of an air mass, we're going to say we have an ether. And instead of sound waves, we're going to have, say, a light source, right? Some source of electromagnetic disturbances. That source could just be a bunch of electrons that get shaken back and forth, right? Accelerated. That's what happens on an antenna. Okay, so the picture, it really does look just the same, but instead of air mass, we'll put ether. Instead of velocity of sound with respect to air mass, we'll have the velocity of light with respect to the ether. And then we can have a velocity of the light source itself, which is like the velocity of the plane. So for light and ether, so light will give the symbol L. For ether, let's give it the symbol lowercase e, and we're going to have as the source, so the light source is Earth. And this has a lot to do with me mentioning a famous experiment referred to as the Mickelson and Morley experiment. Michelson and Morley. These are two people famous for at least doing the coming up with and doing the first experiment of its kind. So here is the idea, right? And it's gonna, like I said, it looks really similar. So this is the ether, and what we're gonna have is the Earth has a little tiny light source on top. Looks like a person. It's not meant to be a person. But the Earth has a velocity. It's the velocity of the Earth with respect to the ether, a lot like the velocity of the plane with respect to the air mass. And let's say it's traveling towards the right in the background ether. So that means that the light source is going to put out light waves that are squeezed in the front, or on the right side, because the Earth is headed towards the right. and these light waves are somewhat spread out in the back. But the light waves travel with a speed, so this is the speed of light with respect to the ether, has the famous value c. So the speed of light with respect to the ether, this is a lowercase e, is equal to roughly 3 times 10 to the 8th meters per second. This is this value c. Presumably, oops, I drew the arrow kind of, unfortunately it's way bigger than the, right? You know that there's something wrong with how big the arrow there is. But anyways, if this is true, then, and light travels on the ether as a disturbance on the ether, so after the light source puts the disturbance into the ether, right, that energetic disturbance, it's carried by the ether and has nothing to do with the source itself anymore. It's untied to the source. Okay, it travels away from the source. But in the front, you can get that the velocity of light with respect to the Earth can be bigger, oops, actually, it's going to be smaller than the speed of light. And in the back, the velocity of light with respect to the Earth is going to be bigger than c. And there are, so this is pretty interesting. So in and of itself, I haven't said enough to say why this is problematic. So what I'm going to do next, though, is I'm going to address, I'm not going to address why or if this is problematic. I'm going to address Mickelson and Morley's experiment. So Mickelson and Morley, oops, I misspelled Morley's name, excuse me. It's Morley, like this. Mickelson and Morley experiment. So they devise a clever experiment to discover, so they take it for granted that this is how to understand light. So the experiment is a naive, well, in hindsight it's naive, it's an innocent effort to discover the velocity of the Earth through the ether. They want to know, how fast does the Earth travel through the ether, right? Is it slow? Is it quick? But what they have is they have a suspicion that the velocity of the Earth through the ether should have a seasonal value. That is, the winter and the summer, for example, these are sort of opposite seasons. The value of the velocity might be pretty different. The point is so they imagine the sun, right? The Earth travels around the sun in this kind of like orbital fashion. And the Earth out here, say, travels, let's say the Earth is going around the sun in this counterclockwise sense. It travels somewhat slow out here relative to the sun, and somewhat fast over here relative to the sun. You get this because of for example, the conservation of energy. As the object gets closer, it loses gravitational potential energy, and the way that loss is taken up in the conservation is you gain a kinetic energy, and then you slow down as you get further away, and then you speed up and then slow down. Yeah, it's called a gravitational slingshot. It's famous in astronaut movies and stuff like that. But anyways, so if you imagine that the Earth changes its motion as it goes around the sun, and actually I think in a sense for the northern hemisphere, this actually is, I can't remember. It's not winter though. It's either fall or spring or something like that. Anyway, right? Because the seasons have, the temperature of the seasons has more to do with the tilt of the axis. relative to the plane of the ellipse, blah, blah, blah. But anyhow, what this gives us is a reason to suspect that in the ether, the Earth might be traveling. So in the ether, it's not necessarily on a fixed elliptical orbit. In the ether, the Earth is going to track possibly like something like this, right? So this is the trajectory of the Earth relative to the ether. The idea is maybe the sun is drifting itself through the ether. That's the sun's ether drift, and the Earth is doing keeping up with an ellipse relative to the sun, irregardless of how fast and where it's at in the ether. Is the suspicion or the sort of concept of the ether. So this is the path of the Earth relative to the ether. So sometimes the velocity of the Earth through the ether it can be quite slow, and then maybe it's quite fast over here, and etc. But what Michelson and Morley find is that, so Mickelson and Morley measure. So it's not that they guess, it's not that they have a hunch, it's that they measure experimentally that the velocity of the Earth through the ether is basically zero all the time. This might be true if, say, the ether was tied to the Earth completely. That is, the Earth sort of carried the ether around it. But the problem is that starts to make the Earth seem, honestly, a little bit too special. So what happens is, and this is kind of the gist, and of course there's a lot of back and forth, and a lot of people try to come up with all kinds of machinations for why this could be true, but there still is an ether. But Einstein comes along and says the simplest explanation is, and I love this, or at least this is how it was presented to me, and I think it's not a bad way to maybe think about Einstein's stance, but the simplest explanation is the ether concept is unnecessary. That is, to keep the ether around as a concept is simply requires too many machinations. It requires too much overhead, too much mental gymnastics. And this attempt to go measure, in some sense, the ether, it's not a measurement of the ether itself. It's a measurement of how the Earth moves through the ether. But this kind of, so all the time means it must not be a seasonal issue. It just must mean that, like the simplest takeaway is that there is no ether. So the ether concept is unnecessary. So why not say there is no ether? Okay. I hope that's okay. So here we go. This is now something Einstein is trying to settle on a new conceptual way to think about light waves, but with an important assumption. And this important assumption is that there is no preferred inertial reference frame. That is, physics has no preferred frame. Okay, so one piece of physics is that the speed of light is 1 over the product. It's actually the square root of the product of the permittivity and permeability of free spaces, that is, of the vacuum. These things are the result of experimental measurements. They are essentially the relationship between electric and magnetic force and distance, charge, and current. So if you do these experiments, you're going to get values for epsilon naught and mu naught, right? You do these experiments, you get these values. And Maxwell gave us a reason, right? Maxwell's equations give us a reason to say that there is a speed of electromagnetic disturbance that is 1 over the square root of epsilon naught times mu naught. So that means that, so we have this. But then, if there is no preferred reference frame, then these values, regardless of the frame of reference, these values will always be the same because they are the relationship between physical things that you can go and measure. So that means that the speed of light should be independent of reference frame. C is independent of reference frame, inertial reference frame, right? And so the idea is we have to rethink relativity and kinematics, actually. In particular, measuring in the dimension of space, that is measuring lengths and measuring time durations, right? So we have to rethink relativity and kinematics with some new starting points. And these are called Einstein's postulates for special relativity. And the postulates, there are 2 of them. So this is physics is independent of inertial reference frame. All such frames are equivalent. And the second postulate, there's only 2, is that the speed of light, so speed of light will always be measured to be the same regardless of frame. So for example, back to the ether picture that I drew earlier, there's a problem, right? This is where the problem's at. Classical problem. So the classical problem is is the speed of light, which we have reason needs to be independent of choice of inertial reference frame. Right here, I just showed you that if you use velocity addition, so classical velocity addition, if you use classical velocity addition, you can find that there will be observers that can measure speed of light smaller than 3 times 10 to the 8th meters per second, and you can find observers that measure speed of light larger than 3 times 10 to the 8th meters per second. So one of the things that we need to fix is we need to fix velocity addition, that it's not as simple as the classical just, with that plus sign. So we need to come up with special relativity velocity addition. But before we get to that, though, we're going to change how we view lengths and time durations. Right? Specifically, there is a concept called length contraction. There is also a time dilation. And then we also need to concern ourselves with a new velocity addition rule. And that's what we'll do in the next video.